Thank you very much. Good morning, everybody. Thank you very much for joining this webinar today. We're so pleased to see so many people. So today, Liz and I, Sarah, I'm afraid, had to send her apologies. We'll be taking you through some of the common errors that we see in meta-analyses.
I can't hear you, Nuala.
Oh, can you not hear me at all? Oh. Can you hear me?
I can hear you loud and clear. We're in the UK.
But others cannot hear me?
I can hear you.
Okay.
I cannot see you. I'm from Canada.
Okay.
I can hear you now.
Oh, you can hear me now?
I can. It was my audio problem. No
Okay. Okay, I think maybe we'll just carry on, and if anyone can't hear me, hopefully they'll write it in the box.
Everyone seems to be able to hear you. Sorry, it was my audio issue. So, sorry,
Okay.
carry on.
Okay, on we go. So the objectives of the session today are to really identify what some of the most common errors in meta-analyses. Obviously, we won't be able to cover every error, but we'd like to go over some of the errors that we as a team seem to see quite frequently. We'd also like to try and show how these errors, even though they're quite minor, can impact the interpretation and the conclusions of a review. And hopefully we'll also go over how best to rectify these problems and ideally avoid making them at all in the first place. So just to give you a little bit of background about the work that we do, hopefully you're all aware of the Messier standards that Cochrane adhere to when they're writing their reviews. But obviously we all struggle to find the time to go through every single one of these standards and ensure that our reviews matches every single one of them. So as part of our job, we have been trying to screen reviews against what we consider to be the key Messier standards for the past 5 years. So this process has evolved, and we ended up developing a tool that considered what we believe to be the 3 core components of a review, and using these core components as the major determinants of the overall quality of the review. So we look at the implementation of protocol methods, whether authors actually did what they said they would do, and if what they had planned to do was appropriate in the first place. We look at how the findings are being interpreted, and also whether the reporting is consistent across all sections of the review. So this tool that we designed looks a little bit like this, really. It's just 4 key questions from Messier that we think overall give a good idea of whether the protocol methods have been implemented properly. 5 key Messier standards that we use to look at how the evidence has been interpreted, and particularly the summary of findings tables and the author's conclusions. And then finally, 5 more key Messier standards that we think give a good idea of the overall consistency of reporting across all the sections of the review. So we were doing this process for a while. For a few years, we were using this tool to assess the quality of reviews before they were published. But people found that this process was quite helpful. Sometimes it's good to have a fresh pair of eyes at the end of the process that can look at the review and can spot some of the problems that maybe were there from the start and just kept being missed, or maybe some problems that came about during the process of the review. So the increase in demand for our work led us to develop a second tool that we called the triage tool. So this tool was more of a high-level tool to help us decide really similar enough sections. You know, again, we're focusing on implementation of protocol, the interpretation of information, and how the information is presented in the summary of findings table, and then also the consistency, particularly in the abstract. And we've been using this tool to get a higher level look at a review and decide, is it actually in trouble? Does it need a closer look using our initial tool? This tool that we've developed now, the triage tool, we find it works really well. The three different sections, though, you can't really look at any one of them in isolation because they all relate to one another. You know, ideally, if all three sections are showing good features of a review, that to us is the indicator of a good quality review that has good consistency and that we're not too worried about. We're happy to go ahead. So the tool itself is based a lot on the Messier standards. So we have reduced it down even further. And we're looking at things like the eligibility decisions, the risk of bias assessment, and how the analyses have been conducted. And you can see these are the Messier standards in purple that these domains really are trying to cover all at once. The summary of findings table triage tool domains are similar. Again, we're looking at how the summary of findings table has been put together, whether it's adequately detailed and whether the grade ratings are justified and sufficient. And then finally, the abstract, is the right information being presented in the right way? Is it consistent? Is it clear? And is it useful, really? But today, what we're going to focus on are the common errors that we pick up using this section. So the first column of the triage tool looks at implementation of protocol methods. And we're specifically going to go over the most common errors we see coming up when we assess these last 5 items in the triage tool. So looking at, do the analyses match with the method section? Are non-standard designs being appropriately incorporated? Have multiple measurements been handled appropriately? Are there any outliers? And if so, are they acknowledged and explored properly? And just in general, are there any data entry errors? So over the course of our work, we have spotted quite a number of common errors that do appear more than once. And we tend to categorize them into one of 3 groups. There's relatively minor errors that we just like to call funny looking results, where when you look at a forest plot and it just doesn't look right. There's an outlier that doesn't make sense, or the study weight doesn't match the sample size. Just something that an initial glance can tell you that's funny looking, as we put it, and might deserve a closer look. But then there's also common errors with the analyses, and these would be slightly more serious errors. So these would be fundamental flaws in the methods and how they have actually conducted these analyses. And then thirdly, unfortunately, there's also the errors that we may not see, because not all errors are clearly visible when you look at a review for the first time. So I'm going to take you through the funny looking results, and then I'll pass over to Liz, who will take you through the analyses and the other errors in more detail. So the 5 most common funny looking results that we see would be data entry errors, study weight at odds with sample size, outliers, studies appearing more than once in a forest plot, the reporting of the results not being consistent with what's reported in the forest plot, and the analyses not matching what was planned in the original method section. So the first one, a data entry error. So this is what we mean by a result that is funny looking. You can see here study 5 and 6 look quite similar. They're both giving the same result, certainly. They're both suggesting that there is an effect favouring control. But it's strange that one of these results, study 4, is so opposite. It's saying favours experimental, and it's not touching the line of no effect. So it seems to be quite certain about this result. So it is strange to see such a difference across the studies like that. And particularly the fact that the heterogeneity, the I-squared, is at 95%, which is extremely high and unusual. And that usually, unless there's a clear reason why study 4 is so different to studies 5 and 6, that would be a reason to suspect there's a problem with the data entry. And in this example, this is taken from a real life example, and when we went to the paper that this study 4 came from, we found that it was a case of data entry error. So if we look at the final row in this table, DOTES, the data that is taken from this table and put into the analyses is placebo versus clomipramine. And you'll notice that what the review authors have done is they have put the placebo mean and standard deviation into the control mean and standard deviation into the experimental mean and standard deviation in the forest plot above. So we have 0.8 with a standard deviation of 1.7. That should appear under control, not experimental. And if this data had been entered correctly, this result from study 4 would switch to the other side of the graph, which would be more consistent with the other studies, and it would certainly reduce the I-squared a lot. So when you see a result like that that just seems to be completely going against the other studies in the review, it's worth double checking to ensure that the data has been entered correctly. Another common error we see is when the study weight appears to be at odds with the sample size. So we have here 2 studies, study 1 and study 2. Both studies are very similar in terms of their sample size. We have 67 participants in study 1 and we have 71 participants in study 2. So usually you would expect those 2 studies to have a similar weight because they are giving the same amount of information. But you'll see from the weight column that study 1 is given a weight of 99.8% and study 2 is given a weight of 0.2%, which seems a huge difference and not easily understandable. Now, the reason for this is, of course, the standard deviations. They are clearly, because the standard deviations also are used to calculate the weight of a study. And you can see there's a huge difference in the standard deviations of study 1 and study 2. And when you see a difference this big, study 1 has a standard deviation in the intervention group of 0.001, but study 2 has a standard deviation of 0.73. That is a huge difference. That to us would indicate another data entry error, really. And in this case, that is exactly what happened. What the review authors did here was for study 1, they had accidentally used the standard errors data instead of standard deviation. So when you see a standard deviation that is so much smaller than the other standard deviations in a forest plot, it's worth checking to make sure that maybe the standard error wasn't taken instead of the standard deviation. Next up, outliers. Now, outliers are a tricky one because sometimes there are genuine outliers. There sometimes are studies that just sit completely aside from the other studies, and there might be a good reason, or it might just be chance. So we can't always know exactly what has caused an outlier. But the important thing in a review is to make sure that the outliers have been acknowledged and at least attempted, that the review authors have at least attempted to account for them and explain why that outlier might be there. So sometimes outliers are quite simple to spot. I think there's one outlier in this chart that everyone could see, and it's this one here. It's clearly the confidence interval of this study doesn't overlap with any other confidence interval. It's very far to the left-hand side. So this would be a definite outlier, certainly something that's easily spotted and recognized as an outlier. And in this case, when we went and had a closer look at the data from this study, we realized it was another situation when the standard errors had been used instead of the standard deviations. And then when the standard deviations were used instead, this was no longer an outlier. It moved back in line with the other studies, and it made a lot more sense. However, there's a second study in this chart, in this forest plot, that we would consider an outlier, and it's not actually as easy to spot. I mean, this one was easy to spot because it's so far out to the left-hand side, but there is another one that we would consider to be an outlier, and it's this study right here. It's smaller and it does overlap the confidence intervals with some of the other studies, which is why it's not as easily spotted. But at the same time, it's the only study in this entire list that not only favours control, but the confidence interval doesn't even touch the line of no effect. So again, this is an example of us that's less easily spotted, but it's certainly saying something very different to all of the other studies in this forest plot. And when we looked at this in more detail, we found it was because the minus sign had been left off the mean. Very simple mistake, very easy to do, very easy to fix as well. And when the minus sign was added back on, then again, it flipped to the other side of the chart, the favours MI side, and again appeared a lot more consistent with the other studies in this graph. Another issue we see quite often is when the study ID appears more than once in a forest plot. So we can see here we have a single forest plot, and it's subgrouped into time points. So we have time point 1, time point 2, and so forth. But clearly the same participants are being used in time point 1 and time point 2. So for example, study 1, the 17 participants are being used again in time point 2. And this is a problem because at the very bottom of this forest plot, we can see that all of these time points have been pulled to create a single pulled effect of minus 0.32. And this is a problem because this effect estimate of minus 0.32 is using the same participants multiple times, and therefore it's not correct. In fact, if we were to take this forest plot and remove all of these time points, so it was just these studies and this final effect estimate, this is what it would look like. And in this way, it's a lot easier to see how many times studies are included multiple times. And as a result, these participants are being double counted in this overall effect. So in this example, if you could have these studies presented at these multiple time points, but the total effect estimate would have to be deactivated because this is misleading and it's including too many participants multiple times. Reporting being at odds with the forest plot. Again, sometimes these are easy to spot. If the forest plot says the effect estimate was 2, but the text of the review says the effect estimate was 4, that's an easy one to spot. But sometimes they're slightly less easy to see. For example, in this case, we have a reporting of the adverse effects that said that higher proportions of participants were reported to experience side effects in the treatment group compared with placebo. Absolute effects of 100% versus 25%, risk ratio 6.04, and the confidence interval goes from 2.67 to 13.65. So if we glance across at the risk ratio, that is exactly what it says. Risk ratio 6.04, 2.67 to 13.65. So at first glance, it would be easy to think that this is consistent with the forest plot. But the feature of this reporting that is not consistent is their presentation of the absolute effects. So they have said that it's 100% versus 25% in the text. But if we look at the actual events compared to the total, for the intervention group, it's 37 events out of 84 participants, which does not equal 100%, versus 5 events out of 80 participants, which again does not equal 25%. So it's important to make sure that all of the reporting is consistent with the forest plot, not just the risk ratios, but any data that is reported in the text must be consistent with what is reported in the forest plot. And then finally, when the analyses don't match with the method section. So sometimes it's just a case of the authors have planned something in the methods, and then when we get to the results, they have not done that. But more than that, they have not explained why they haven't chosen to do that. So for example, we would frequently see something like this in the method section. They'll say, when study authors use different measures to assess the same outcome, we converted continuous outcome data into standardized mean differences, which would be an appropriate method to do. And then You might see an analysis like this, which is measuring change in weight as measured by kilograms. And you'll notice that they're using standardized mean differences here. But this appears to be inconsistent with their plan, because if, as the title of the analysis states, all of these studies were measuring weight in kilograms, they're measuring the weight in the same way. Therefore, it wouldn't be necessary to use standardized mean differences. So there's clearly either a problem here that they are not adhering to the plan they had laid out in the method section, or it could be that each of these studies did not measure it in kilograms. Some measured it in kilograms, others measured it in stones, and in which case maybe it would be appropriate to use standardized mean difference. But at this point, these analyses don't match the methods, therefore it would need to be highlighted and addressed. And then finally, it's important to remember that sometimes the analyses don't match the methods, but sometimes there's a good reason for that. It could be that the methods that were originally planned in the protocol have since evolved, and there's now a more appropriate way of managing the data. Or it could be that there was some aspect of the review that review authors were unprepared for, and they had to update their methods to incorporate that. So there are, analysis can be different to the method section, but the important thing is to make sure that the review authors have explained and justified any changes to the methods from the protocol. A good way of spotting that when a method might have changed is by going into Archie and opening the History tab of a review and selecting the protocol of the review and the current version of the review that you're looking at, and selecting the Compare function. And then what you end up with is a PDF that looks like this, that will highlight any changes that have been made between the protocol and the current version, with green text indicating that something has been added and sections that have been deleted ruled out in red. So this is a good way of just going through and seeing, has the methods section actually changed altogether? And if it has, it's really important to outline and justify any of these changes in the section of the review, differences between protocol and review. It's not enough to just outline the changes have to be justified. There has to be a clear and reasonable description of why it was necessary to change those methods. So those are what we would call our funny looking results. And now I'm going to hand over to Liz, who is going to take you through the some of the more in-depth analyses and errors that we see there.
Hi everybody, so hopefully you can now see my screen. Sorry, I had a bit of a technical issue there. So as Nuala said at the beginning, we do see some common errors in the implementation of the analyses, and these are more of a fundamental problem than the funny looking results that Nuala has just run through. And the four things that we sort of most commonly see are problems with unit of analysis, so whether crossover trials and cluster trials are being incorporated into the analyses appropriately. Also, implementation of subgroups. This is quite problematic in a number of reviews. Often subgroup analyses are conducted post hoc without any clear justification why, and sometimes they're incorrectly interpreted and ignore the results of the test for subgroup differences. Often subgroups have insufficient information in them, and that's not always taken into account when authors are interpreting the results of any subgroups they've performed. And also, sometimes it's helpful to specify upfront in the protocol the subgroups that you're going to be applying, but also to which outcomes those subgroups will be applied. And it's not always appropriate to apply it to absolutely every single outcome in the review, and it's probably best to focus on the primary outcomes. Third problem that we sort of see quite commonly is use of standardized mean differences and mean differences, and sometimes these are used incorrectly. and standardized mean differences aren't often re-expressed on a common scale for people to understand. For example, sort of Cohen's rule of thumb, or a sort of frequently used scale for sort of quality of life, for example, the SF36. And then the fourth thing that we see problematically is the random versus fixed effect model, and an inconsistency with what's specified in the methods and actually what's been performed by the authors. So, I seem to not be able to, there we go, move on to the next slide. So the first thing really is unit of analysis problems, and the main, I'm going to focus on cluster randomized trials, but obviously crossover trials also have unit of analysis implications. But I'm just going to address the cluster randomized trials here. But for information, I would recommend, if you're dealing with crossover trials, that you read the section of the handbook which deals with how to incorporate crossover trials in reviews, and that's section 16.4. I read it quite frequently. And so, but here we're going to talk about cluster randomized trials. So this is an example where the authors have specified that they planned to extract estimates of effect that took into account the correlation of the measurements. And this is important because in cluster randomized trials, the unit of randomization is the cluster and not the individual, and therefore the analysis has to take account of that. Guidance in the handbook around how to incorporate cluster randomized trials is in section 16.3, and it's very good and helpful guidance. And if you're including cluster trials, you really should be consulting that section of the handbook when you're writing the protocol and dealing with incorporating the data in your review. If authors don't follow their guidance, but instead analyse a cluster trial in the same way as an individualised randomised trial, the confidence interval for the treatment effect will be artificially narrowed because the clustering is not taken into account. So interpreting unadjusted analyses may lead to false conclusions. Authors really need to adjust the effect estimates from cluster randomised trials using estimates of average cluster size and the intra-cluster correlation coefficient, and this quantifies the extent to which the data from observations within the same cluster are correlated. So in this example, it's quite difficult. These are difficult things to spot. They're not exactly like the funny looking errors that Nuala was talking about. You can't just look at this forest plot and know whether the data have been analysed correctly. It takes a bit of detective work. So in this example, because the authors have included cluster trials, it's worth going and checking that this data has been adjusted. And one way of doing that here is to look at whether the total sample sizes have been adjusted appropriately. So we would expect, if they had been adjusted to take into account the clustering effect, the sample sizes for the studies would be smaller than would the sample sizes that are actually stated in the characteristics of included studies. And when we looked at the characteristics of included studies, and the authors had obviously specified the number of participants in each study, in each arm, it was clear that this analysis hadn't taken into account any adjustment for that. And also, it's worth noting when you're incorporating cluster trials that for clarity, you should really incorporate a footnote for the forest plot to explain the adjustments that you've made to take into account any clustering effect. The second problem that we tend to see is implementation of subgroups and the comparison of subgroups. It's very important that you use the formal statistical test to compare subgroups. And in this example, the authors clearly haven't done that. So if we look at this forest plot, you can see that the first subgroup shows a clear effect of 0.77 and is on the far one side of the null line. The second subgroup, obviously the confidence interval incorporates null, and the pooled effect estimate excuse me, is 0.79 and shows an effect. So in the abstract, the authors had stated that the review, excuse me, suggests that the intervention may have more beneficial effects in this subgroup. And also in the plain language summary, the interpretation said, in the further analyses, there is evidence indicated that the effects of the intervention in reducing this particular outcome may be different in subgroup 1 and subgroup 2, with more benefits observed in subgroup 1. That's not necessarily the case, because the test for subgroup differences here, the p-value is 0.6 and the I-squared is 0%, and so this test is demonstrating that there is no difference between these two subgroups, so the interpretation that the authors have given here to the subgroups is placing far too much weight on this particular result here. The third thing that is problematic sometimes is the use of mean difference and standardized mean difference. So the authors had stated in the methods that they will convert continuous outcome data into standardized mean differences and present them into 5% confidence intervals. So assume that study authors will use different measurement scales, and that's an appropriate method. If continuous outcome data is recorded using the same measurement scale, data will be converted into mean differences. And again, that's an appropriate method. When we looked at the forest plot, however, there was a single study for this outcome, and it had been reported as a standardized mean difference. But single study, it's a common scale for this one study, and so really this should have been presented as a mean difference rather than a standardized mean difference. And then the fourth problem that we often see is inconsistency between what's stated in the methods and actually what's implemented. And so in this instance, the authors had stated that they would use a random effects model where the I-squared was greater than 30% and T-squared is greater than 0, or there was a p-value less than 0.10 in the chi-square test for heterogeneity. If substantial heterogeneity was identified, they would use a random effects model instead of a fixed, instead of the fixed effect model. And if you can see here at the bottom of the forest plot, the heterogeneity does not meet any of the criteria that they had specified here. So the I-squared is 22% rather than 30%. The p-value is 0.26 rather than 0.010. And so they've applied a random effects model where the data actually don't meet their specified rule for employing use of a model. And additionally, we see that quite often that people use sort of arbitrary cutoffs of I-squared as a kind of indicator of heterogeneity and whether they would use a fixed effects or random effects model. And that's actually discouraged in the handbook. And the reason for this is that using a random effects model that's kind of being wedded to a use of a model on the basis of heterogeneity isn't always appropriate. So there may be instances where there's evidence of small study effects, and using a random effects model will actually give far too much weight to those studies that are showing, biased results. And so we want to be able to use the appropriate model where necessary. And so in some cases, it's probably better to think clearly about which model you want to use rather than using arbitrary cutoff of I-squared. And then, of course, there are errors that we may not see. These include things like have any papers been missed, and that's almost impossible for us to identify from the screening work that we've been doing. But we have to assume that this is a possibility. Have the right results been copied from the papers? And as we've seen, that it's quite easy to make sort of transposition errors, and copying results from papers is the first step in that, and so obviously if there's an error there, it can be difficult to that error can be sort of perpetuated without you even realizing. So care at that very first stage is really important. And then also have the standard deviations being confused with standard errors. Again, this is something that Nuala highlighted a couple of times in her slides about funny looking errors. Sometimes it's easy to spot you know, a standard error compared to a standard deviation in a forest plot because the standard error will be much smaller, but it's not always very easy to pick those out, and so it's important that the data checking steps occur at the beginning of the process before you kind of continue to perpetuate any data extraction errors. And then we just wanted to highlight some errors that we sort of see in the interpretation and conclusions of reviews, and so often we see interpretation that emphasizes the effect estimate over statistical significance. And so in this instance, the main results stated that for the outcome of mortality at the end of follow-up period, there was no statistically significant difference between the intervention and control groups, with the relative risk of 1.46 and the confidence interval 0.99 to 2.13. And so you can see that the confidence interval includes null, and so there is, you know, no statistically significant difference there, and that is the correct, you know, that's not an incorrect statement. However, looking at the the summary of findings table, we take into consideration the absolute effects here, which for mortality are really important. You can see that the confidence interval here for the absolute effects actually sort of indicates that there probably is an increase in mortality in absolute terms. And so really, rather than concluding that the current evidence does not show a risk in mortality, a more appropriate conclusion or could be intervention Y may increase mortality by 4%, and then specifying the low quality evidence. Again, we're not certain, but I think it's important that the absolute effect is demonstrating something here that is not always captured by the relative effects, and that's important to bear in mind in the interpretation. And again, it's important to capture any uncertainty in interpreting results. And so here we can see that the pooled effect estimate crosses the line of no effect. And so these are very small studies as well. We've only got 2 studies with sort of relatively few participants. And so stating that, you know, analysis provides evidence that the intervention has no effect, this might be, it doesn't take into account some of the uncertainty that is present here and the lack of information that we might have. And a more appropriate interpretation would be that analysis 1.2 provides uncertain evidence whether the intervention has any effect. This is quite a fun slide that sort of indicates the use of language people sometimes try and kind of use to communicate what they think is a borderline significant result. And so focusing on significance, it can be really problematic because people are always trying to meet that threshold and come up with some very colourful language to describe that, and how helpful this is, you know, really is not. It's not particularly helpful. I think it's probably better to focus on the certainty or uncertainty in the evidence rather than potentially just about to meet an arbitrary cut-off of significance. And so instead, we would encourage authors to use this framework that's been put together by Claire Glenton in Cochrane, Norway, along with consumers consumers and communication group. So this is a sort of a nice table that sort of illustrates how you can marry the grade quality ratings with some language around your results. And so where you, for example, where you have evidence that's of an important benefit or harm, and that evidence is high quality, then you can be sort of fairly certain in that result, and so improves feels like a word that kind of communicates that sort of level of certainty. And then for moderate and low, we use terms such as probably and then may. And then when we're dealing with sort of very low quality evidence, really what we're talking about is that we're just very uncertain about the effects of this intervention on a particular outcome. And I think it's important that that uncertainty is sort of clearly communicated to readers. And then we just wanted to close with some final tips for spotting errors that we've come up with. So numbers that stand out are really important. So anything that looks funny in a forest plot probably is worthy of a double check. It may be that that's the correct data that's been entered, but it's worth double checking. For non-standard randomized controlled trials, we want to be sure that the data have been appropriately adjusted, and so it's important to check the methods against what's in the forest plot and also what's in the characteristics of included studies. For primary outcomes, we suggest sort of selecting the biggest study or the one that has the most weight, and just check the analysis against the results of that paper as kind of like a very first sort of basic check to make sure that, you know, things are sort of stacking up correctly. And then for other outcomes, you know, if you've got a large review, you might just want to pick a study at random and sort of just check that what's in the trial report matches what's in the forest plot in the data. And if there's, you know, if the authors have stated that they've got unpublished data, then, you know, move on to the next study because you won't be able to check that. And then, you know, just select an appropriate number of studies to sort of make sure that you think everything that's in the review sort of stacks up. And then finally, we did just want to introduce some work that we've been doing with the training team and the central training team to develop some resources for online learning around common errors. So this is a really kind of quite comprehensive module of training that has been developed, and so this is the website, and I'd encourage everybody to dive into this. It's really got some very useful examples of things that are common errors that we've seen through our work. And the training team have obviously developed sort of links to the handbook and explanations for how to avoid these and why they're problematic. So it includes modules on grade and interpretation of findings, interpretation of statistical results, inconsistency and inaccuracy, summary versions of the reviews, and then there's some elements where you can sort of check your knowledge and do some sort of fun exercises there to spot some errors. So I think, yep, we've just got some resources finally, but I think we're going to open up to any questions. It was quite a rapid flick through some of the things that we've sort of seen over the last sort of 3-4 years of our work as editors within the central team. So if there are any questions, we're happy to try and help. I should point out that neither Nuala or I are sort of statisticians. We're sort of more methodologists, so we will try and help, but we do have a statistician centrally in our team, so if there are any kind of complex questions that we can't address, we'll take them away to the team and get back to you, but we're happy to try and help if we can.
Thank you, Liz and Nuala. The presentation was great, and lots of good tips for us as authors and also as peer reviewers. So if anybody has a question, you can either type it in the chat box or you can unmute yourself and ask the question.
Hello, hi. It's Steve Allen here from Liverpool with a couple of my colleagues. Can you hear me okay?
Yep.
Great. Thank you very much. Really valuable presentation, really helpful. So thank you for that. Just one question. It's about when do you have enough data to do a subgroup analysis? Mm-hmm. We're currently doing a review. We're updating our review of probiotics for the treatment of acute diarrhea. And we pool all the results together across different probiotics on the basis that we're looking for general effects. Yep. But we also want to look at, is one particular preparation you know, what's the evidence for a single preparation? And we've kind of said, as a rule of thumb, we would do a subgroup analysis if there's 5 or more trials. But that's kind of picking a number out of the air. And I don't know if there's any guidelines on what is enough data to do a subgroup analysis.
That's a very good question. So I think the general, there isn't really a sort of written, you know, you must have this amount of data rule. I think in general, it's recommended that around 10 trials per subgroup would give you sort of sufficient information to make a good good conclusion. But I think it also depends on then how you interpret that result. So, I mean, we've certainly seen reviews with subgroups with a lot fewer trials. And I think the thing to be careful of is the interpretation of the results. So, you know, bear in mind that subgroup analyses are purely hypothesis generating. They can't tell you, you know, that there is a definite effect in this group, but not in another. And so I would issue caution in terms of, you know, obviously 5 studies sounds probably, you know, not bad, but, you know, I wouldn't hang my hat on any kind of result that showed a difference in one subgroup but not another, and that probably needs to be reflected in what you write. I don't know if Nuala, what do you think?
Yes, no, I agree. I think with subgroup analyses, our standard line is always with caution, because they are very tricky to do and they can be easily misinterpreted. And I know it's a frustrating answer, but a lot of the time it depends. You know, it depends on the review that you're looking at, and in particular the outcome that you're thinking of doing a subgroup analysis on, how important that outcome is, how important it is to do a subgroup analysis. But yes, I mean, if in doubt, I would say, you know, I prefer to not see subgroup analyses than to see a review that is filled with uninformative subgroup analyses. But yes, unfortunately, it's, you know, as long as you do exercise a lot of caution and you ensure that if you're describing your subgroup analyses in the review, you're reflecting how uncertain results from any subgroup analysis are, then that should be fine.
Okay, thank you. That's very helpful. Thanks. We actually picked 5 on the basis that we know that will probably really limit the number of subgroup analyses that we'll do. Because I think you're right, we prefer not to do them. So that's very helpful. Thank you very much.
Yeah, that sounds like a good approach to me, I think.
Yeah.
Thanks, Stephen. Any other questions? Okay, so if we have no other questions, just thank you again, Nuala and Liz, for doing the webinar for us. This was great. Thank you so much. And thank you, everybody, for attending.
Thank you very much. Bye now.
Bye-bye.
Bye-bye.